Hi guys, this video is about calculating entropy changes for systems, and later I will show you the calculations for entropy changes for the surrounding, which is much simpler than this. So now let's look at this. The formula given here is entropy changes for a system. Okay, this should be labeled as SYS. This is the entropy change for the systems, where we use the total entropy change of the products minus the total entropy change of the reactants. So it's product minus reactants. Okay, so let's say, for example, for these particular reactions, combustions of methane plus oxygen, you get carbon dioxide and water. So what happened to its entropy changes for the system? So these are the table given. This is the table given for the entropy changes for each of the compounds involved or elements involved. CH4 in the gaseous state will have its own entropy value, oxygen as well, carbon dioxide, and water. So these will be all the respective entropy change values. Notice that the unit is joules per Kelvin per mole. Okay, and that's important because when you give your final answer, you should state together with its value. All right, now how do we do that? It's very simple, straightforward. We're going to use the formula. In this case, I'm going to show you the calculations. All right, so first we're going to calculate the total entropy change of the products, which is carbon dioxide and water. So what will be the value for carbon dioxide? It's actually 214, and I only have one more, so leave it as this value, and then 2 water, so 69.9 multiplied by 2. So we're going to add up these two values to get the total entropy change of the products. So 214 plus with 69.9 multiplied by 2, 353.8. So the total entropy for product is 353.8, and the unit will be joule per Kelvin per mole, or per mole per Kelvin, up to you. Okay, that doesn't matter. So then we're going to calculate the total entropy of the reactants. So we have 186 here for methane, and we have oxygen, which is 2 moles, so 205 times 2. So sum it up, 186 plus 2 multiplied 205, 596. So the total energy for the reactants is 596. So according to the formula, we should use product 353.8, all right, minus the reactant 596. Then we get the total entropy change for the system. So 353.8 minus 596. Then we got a negative value, negative 242.2 joule per Kelvin per mole. All right, so what does it tell you about negative entropy system? Can I say, since we get the negative values here, so this reaction, this combustion reaction, is not spontaneous, it's not feasible? Not yet, because like I said, to determine whether a reaction is feasible or not, we need the total entropy change, which include the entropy systems as well as the entropy surrounding. So next, we're going to look at how to calculate entropy change of surrounding. So I guess this is quite straightforward. Product minus reactant, you will get the entropy of the system, which is negative 242.2, right? So the next one is showing the formula to calculate entropy change of surroundings. So how to calculate entropy change of surroundings? We need the enthalpy change for the reactions. All right, so just now the reaction was combustions of methane. Let's say, for example, the enthalpy change is definitely exothermic, right? Because it's combustions. So let's say the enthalpy combustions of methane is negative 1222 kilojoules per mole, right? So this is the enthalpy change. And what is this? This is actually the temperature of the system. All right, and then don't forget, we have a minus sign here, negative the whole thing. Look at that. If we have a minus sign here with an exothermic reaction, which is negative values, negative, negative, you will get a positive. So overall, the entropy surrounding will give us a positive value, right? Without calculating it. So just looking at the sign, we will definitely get a positive value. All right. So of course, it can be a very small value depending on the temperature. So let's say we get a positive values for surrounding. So here is positive value for the surrounding, and then we have entropy system where we have calculated just now is actually a negative value 242.2. Then we will get entropy of total. Okay, total entropy change. Now it depends on whether the positive value here is big enough. It's bigger than 242.2. Then we will get a positive total entropy change. If the positive value here, the entropy surrounding, is smaller than negative 242, so this will give us a negative overall. So the entropy total will be a negative value, which indicates the reaction is not feasible or non-spontaneous. So now it depends on both values. So we can't make a conclusions like just now with just entropy system. Even though the entropy system is negative, if the entropy surrounding is a much bigger value, a positive value, then the entropy total will be positive. Otherwise, it will be negative. So it depends on both values. So this is how we calculate the total entropy change. All right. So for an exam, the question might ask you to calculate the entropy change of a reactions. When they said entropy change of a reactions, then they give you an equations. This is always referring to entropy system, even though they don't specifically mention system. That is always referred to system. But then for surrounding, they will say calculate the entropy of surrounding, or they will just say calculate the total entropy change of these reactions. Then you should know you should include both systems and surrounding in order to get the answer. All right. Of course, the temperature should be given, and the enthalpy change, either they ask you to calculate beforehand or is a given value. So make use of the information to calculate the total entropy change. All right. So that's it. The calculation for entropy change is very simple and it's a short video. So please try the example given in OL, and we will discuss it if you need help during the tutorial sessions. All right. Thank you.